like to start with just a brief kind of recap of what we did yesterday or Monday, excuse me, and then we'll kind of continue and extend it in a way. So somebody pick me a number that's, say, less than 200, and that's an integer. 199. Okay, that is in fact less than 200. You must have been doing some prices right recently, right? Okay, so let's take 199. How would I write that as a binary number, okay, in base 2? And furthermore, unlike what we did last time, this time let's specify in advance how many binary digits or bits we will permit ourselves to use. And for sake of demonstration, we'll use 8, okay? This is one reason I said pick something less than 200 so that I know that it'll fit into 8 bits. So on a computer, a modern computer, you would do this with 32 or maybe 64 bits, depending on what kind of data you were dealing with. And there's really nothing different about doing it with 32 or 64 bits, except there's more of them. Everything else is the same. It's just more of it. Okay, so if I want to write 199 in binary, well, first off, I need to put, what are my place values? Okay, so I have a bunch of the place values are the powers of 2. Okay, and you may not think in powers of 2 like this, so let's just write what those are equivalent to. This will be 1, 2, 4, 8, 16, 32, 64, and finally 128. Okay, so those are the place values for each of the positions of a binary number. Okay, and it just keeps going up by powers of 2. In this case, I've stopped at 8 bits, just again for sake of demonstration. Okay, so we're cool with that. Yeah. Okay, so now what we need to do is, in order to encode 199, we've basically got to say, all right, 128, does that go into 199? Yes, once. With how much left over? 71. Okay, so 71 is now our leftovers. Does 64 go into 71? Yes. With how much left over this time? 7. Okay. Does 32 go into 7? No. So I'll put a 0 here. Does 16 go into 7? No. Does 8 go into 7? No. Does 4 go into 7? Yes. Once with 3 left over. Does 2 go into 3? Yes. Once with 1 left over. Does 1 go into 1? Yes, once with no leftover. Okay, and there should be no leftover by the time you're done. If there is, you've messed up. Okay, so this is the binary encoding of 199, right? So I could write uint8. Okay, and I'll explain what the uint and the 8 are in just a second. Okay, so we picked essentially randomly a base 10 number, 199, okay, and we have now encoded it as a uint8. Okay, now let's what do I mean when I say uint8? Well, what's the 8 part mean? What do you think? The number of bits, right? So there are 8 bits, and that's why I wrote the 8 there. Okay, what kind of numbers are we dealing with here? Well, we're dealing with integers, meaning whole numbers. Okay, not decimals and stuff. We'll deal with that starting on Friday. Okay, and then the last thing is, what does the U stand for? That stands for unsigned integer 8 bits. Okay, so the U stands for unsigned. meaning that we're not worrying about the possibility of there being negative numbers at this point. That's what we'll do later today. Okay, is how to get the negatives into the system. Okay, so if we had, if we have a base 10 number and we want to convert it into binary, that's the procedure. Okay, and if we want to go the other direction, well, then we just write the number down. And so, like in this case, I would say, all right, this number is a 128 plus a 64 plus a 4 plus a 2 plus a 1. Do the arithmetic, and then lo and behold, what do we get? We would get 199. And that's a good thing because that's what it should be, right? That's what we started with. Okay, so does that make sense? Okay, yes, Liam. 0B in front of something indicates that I'm writing that thing in binary, right? Because how do you know that I didn't write, that I didn't mean 11,111,000, right? You don't. Okay, and so if I put 0B in front of something, that's just code for, hey, I'm representing this in binary. And what about if I wanted to write it in hex? What would I put in front? 0x, okay? So that's just the convention so that you know what system I'm writing in. Okay. Okay, so is that cool? Yeah. Okay, so let's take, this is a perfectly good number. Pick another number that's, again, less than 200. 83. Okay, thank you for not picking the number that I'm sure everybody was thinking. Okay. All right, so 83. Let's do the exact same thing for it. Okay, in fact, you guys do it. And so take a couple of minutes and figure out what it is, and then you will tell me it's binary representation, and I'm sure everybody will agree with this. Yes. You done already? So do what we just did with 199, but with 83 instead. Yes, because we're doing this in 8 bits. Okay. Well, for unsigned numbers. For signed numbers, there'll be a slight difference, but we'll get to that. Okay, did you guys get this? Okay, so we agree. All right, good. Okay, so the reason I picked a second number, A, just as an extra piece of practice, but B, because so we can do something. Because if I've got two numbers, what could I do if I've got two numbers? If I got just one number, okay, great, I got a number, yay. But I got two of them, we could do math, right? We could add them or subtract them or whatever, okay? All right, so what were our two numbers again? 199 and 83. I'd like you guys to add those together, okay? And do this like you did in grade school. So what's 9 plus 3? 12, so 2, carry the 1. What's 9 plus 1 plus 8? 18, so 8, carry the 1. What's 1 plus 1? 2. Okay? Wow, you could have done that in what? Third grade? Second grade? Yeah? All right, let's do the same thing in binary. All right, so 199 was 110000111, and 83 was 010101. Sorry, 0011. There we go. Okay. All right. So what's different here, okay, is, well, I've only got two symbols, 0 and 1. Okay. So there's four possibilities of additions that I could have. I could have 0 plus 0, and shockingly, guess what that is? 0. Okay. 1 plus 0 is, okay, 0 plus 1 is 1. What's 1 plus 1? Okay, we would say 2, but really it's 0 carry a 1. Okay, in the same way that what's 9 plus 3? 12, but we write 2 carry a 1. Does that make sense? Yeah? Okay. So what's 1 plus 1 in the far right-hand position here? 0 carry a 1. Okay? And then here we have something interesting. We got 1 plus 1 plus 1. That's, what do you think? 1 carry a 1, or 3, right? So 1 carry a 1. And then what's 1 and 1? 0 carry a 1. What's 1, 0, and 0? 1, no carry. And then 1, 0, 0 carry a 1, 0 carry a 1. And something interesting just happened. Okay. Okay, so the carrying system is exactly the same as it is in base 10, except you've only got 2 bits. That's it. Okay, so if I were to do this, so let's take, well, in this case, okay, 199 was a 3-digit number to start with, but if I give you, say, two 2-digit numbers, it's perfectly possible that you add them and get a 3-digit answer, right? Right, that just happens. Okay. And what happened here is we had two 8-bit numbers, okay, and there was a carry in the final position that I've kind of boxed in orange here. Okay, so this is where computer arithmetic and human arithmetic differ. If I gave you two 3-bit number or 3-digit numbers and you added them together and you got a 4th digit, you just write it down. Okay, it's a 4th digit, great. Okay, but what did we say in the beginning when we were doing this with the binary stuff? We choose in advance how many bits we're allowed to write down. Okay, and for sake of demonstration, we'll just use 8 bits. Okay, 8 shall be the number of the bits, and the number of the bits shall be 8. Okay, 9 is right out. You guys have all seen Monty Python, right? The Holy Grail, right? When they've got the instructions for the Holy Hand Grenade of Antioch, right? Counteth unto 5 or 3, excuse me. No? If you have not seen Monty Python and the Holy Grail, you have an assignment this weekend, which is to go watch it. Okay? Trust me, you'll like it. Okay? Okay, so in advance, I decided that we would use 8 bits. Okay, but I got a carry in that 8th position. That carry is the one that I wrote in the orange box. Where does that go? If I say, thou shalt use 8 bits, where's the one going to go? Poof, it's gone. It just disappears. Okay, so that may seem weird, okay, and it is. So I'll explain a little bit here. First off, we've got a binary answer, right? So this binary number, what does that represent? Well, do I have a 1? No. Do I have a 2? Yes. Do I have a 4? No. Do I have an 8? Yes. Okay, so 8 and 2 is 10. And then do I have a 16? So what does all of this actually look like? Looks like 26. Yes, 10 and 16. But what answer were we expecting to get? Yeah, if we just did this like we did in grade school, we would have expected to get 282. Okay, what I want you to notice is how could I write 282? Is that true? Is 282 256 plus 26? Oh, that's interesting. Okay, so what happened here is a phenomenon called overflow. Okay, and let's return to the clock analogy that we were talking last time. Okay, so again, just to remind ourselves, humor me and let's pretend that the 12 on the clock is actually a 0, but otherwise everything's the same. Okay, if I ask you what is 7 plus 8 on the clock, what would you respond? Okay, you would respond 3, not, no, wait a minute. Sorry, you would respond 1. Okay, what's 7 plus 8 normally? Oh, wait, okay, sorry. I'm sorry, guys. As a mathematician, one of the things that we are terrible at is doing arithmetic. If I was good at arithmetic, I would have been an accountant. Okay. So, like in elementary school, I really did not care for math. I was okay at it, but I was way more interested in science. I mean, think about it, right? Why would you could do a bunch of math or you could blow stuff up. Which would you choose, right? um, yeah. So, okay, so let's try that again. What's 8 plus 7? 15. Okay. Normal arithmetic, grade school, right? 15. Okay. But 15 doesn't exist on the clock, does it? So if I start at 8 and I go 7 positions beyond it, then 9, 10, 11, 0, 1, 2, 3. Okay. So do you guys accept that in this sort of clock world, 8 plus 7 is actually 3, not 15? Yeah. That's exactly what happened here with uh, our answer of being 26. Okay. The only difference between it and the clock is the clock that we're working with in our 8-bit system has, imagine it's like a regular clock, but with 256 different positions, 0 through 255. Okay. And if you exceed 255, you just start the circle back over again. Okay. That's a weird system of arithmetic. Has anybody ever seen or heard of modular arithmetic before? No? Okay, that's basically what we're doing. Computers work in a modular system. Now, furthermore, what I want to point out is notice that, well, what's the remainder of 282 if I divide it by 256? 26, right? What's the remainder of 26 if I divide it by 256? Well, 26, because 256 can't go into 26, it's too big, right? So 282 and 26 are in some sense the same number because they have the same remainder upon division by 256. Okay, and why is 256 so special here? Well, how many bits are we using? 8, and what's 2 to the 8th? 256. Okay, so we are working in a clock that has 256 little things. Okay, complete with the sound effect, and you don't do this sound effect; it doesn't count. Okay, yes, Liam. So you don't indicate at all. Well, okay. Maybe you just write or notate this in English, like, "Hey, overflow just happened," right? And on in computers, um, oops, that one or the fact that overflow just occurred is actually stored someplace. There's a little, so processors have a thing in them called a flag register, and if an overflow occurs when you do an arithmetic operation, a flag goes up and, hey, overflow just happened, and then you could make decisions based on that. Okay. But yes, it's just to note that overflow did occur. Okay. So this is basically the problem that, remember last time we talked about the Gangnam Style video, right? Where the play count got screwed up. This is exactly what happened, but on a smaller scale. Okay, because they were using 32 bits, and so the biggest number they could represent was like 2 point whatever billion. Whereas here, the biggest number we can represent in 8 bits unsigned is 255. Okay, and why 255? Well, how many patterns are there if there's 8 bits? There's 256 of them, right? So why is 255 the biggest number that we can represent? Because 0, right? We have to count that one. And it would be good to have 0, right? That's certainly a logical number to be able to encode. Okay, so does that kind of work? All right. So I promised you guys a magic trick last time. Okay. So here we just added 199 and 83. Could I have subtracted one from the other instead? Yeah, sure. Okay, so let's go over and we're going to do 199 minus 83. We'll first do it the way that you did in grade school, and then I'll show you the magic trick. Okay? And don't worry, it doesn't involve any hats or people in boxes that are getting sawed in half or rabbits or any other, critters. Fine. I may not impress Penn and Teller, but actually it would be kind of fun to go on their set and do like a bunch of mathemagic and see if I can fool them. Huh? Oh, magic. Yeah. Well, first we're going to do great. We're going to do this the right way, and then we'll do it the magic way. All right. So if you were back in elementary school and you had to do this, you would say, okay, 3 from 9 is 6. Okay, great. 8 from 9 is 1, and 0 from 1 is 1. So the answer is 116. Yay. Wonderful. Okay. All right, let me take the number 83, and I'm going to do something to it. Okay, I'm going to take all of the digits, and I'm going to pair them up. I'm going to pair 0 with 9, 1 with 8, 2 with 7, 3 with 6, and 4 with 5. Okay, so just trust me. I'm the magician, not you. Okay, all right, so let me take the number 83. And I'm going to mirror the pairs. So what's 8 paired up with? 1. What's 3 paired up with? 6. Okay. Add 1 to that. So I get 17. Okay. So I took each digit and I replaced it with its pair, its mirror. And then I added 1 to it, just because. Right. All right. Now, let me take 199. Okay. And I'm going to take, oh, shit. Hold on, guys. I forgot something. The number that I'm subtracting is really 083. So let's back up a minute. What is 0 paired with? 9. So what really should I have had? 917. Okay. So 917, okay, is my sort of bizarro number. Let me add that to 199. All right. Good. All right. What's 9 and 7? 6, carry a 1. Then what do I have? 1, carry a 1. And then what do I have? 1, carry a 1. But again, I'm going to discard that. And lo and behold, what do I get? 116. Right? And you guys pick the numbers, not me. right? So you can't accuse me of cherry picking or anything, right? Okay, so that's my magic trick for the day. Kind of clever. Okay, so this magic trick is not just pulled out of thin air. Well, maybe it is, right? It's a magic trick, so I've got to pull something out of thin air. What I have done here is this mirrored version is called the nines complement. And when I add 1 to that, that's called the tens complement. Okay? And what we're going to do with binary is essentially the same magic trick, but it actually is easier in binary. Okay? All right. So, first off, let's pause. Questions about the magic trick, other than why did it work? But because I can't give up my secrets, man. Come on, I'm a magician, right? But yeah, go ahead.
I'm just gonna ask
Because I know I have to, right? Because it works. It doesn't work otherwise. You have to add the 1 for it to work. Okay. And now this does really beg the question: why the hell does this work at all? Okay, and I could prove that to you guys, but again, that would be revealing my secrets, and that's just not done in the world of magic, right? Yes. Okay. So I should, yes. Okay. I'm not going to now because I don't want to sidetrack us from the discussion, but yeah, I could prove why this works. Okay. Um, and every now and then, right, you get some interesting ones like maybe these things go around on Facebook periodically where it's like, take the date of your birth, do this, add that, multiply it by this, subtract something, and then I bet you got 7 as your answer or whatever. And the thing is, you always get that number, and you could sit down and prove why that happens. And nothing will get you unfriended on Facebook faster than explaining to people why the math works out that way. Um, Definitely don't use it as a pickup line. Okay, it really, really will not work. Yeah. Okay, so let's take the two numbers that we did here in binary and do the same thing. Okay, so what was it that we had 83 in binary? Okay, so it was 0, 1. Say it again: 0, 1, 0, 1, 0, 0, 1, 1. Okay, so what basically I have done here, the trick that I've done is I wanted to think of how to do 199 minus 83. Okay. And that's a perfectly logical mathematical operation to do. You guys have been doing subtraction since grade school, no big deal. Okay. But notice that with this trick, I was able to do the problem without actually doing subtraction. What I did was I turned it into an addition problem. So instead of thinking of 199 minus 83, I'm going to think of that as 199 plus negative 83. Okay? Same thing algebraically, but it's just by thinking of it in that slightly different way, we can be devious. And that makes it more fun, right? Okay. So what I'm going to say here is that 917 is the tens complement representation of negative 83. They're somehow paired in a way. Okay. Um, okay, so we're going to do sort of the same thing. I mean, we're working with the same numbers, but we're going to do this in binary instead of base 10. Okay, so one piece of lingo. Well, can we talk about 9 or tens complement if we're working in binary? That doesn't make sense. There is no 9 or 10. Okay, so instead we call this 1 and 2's complement. Yeah? I mean, that's just logical. Okay, so the other thing is what was the key to the magic trick was sort of that mirroring of the digits. 0 mirrored with 9, 1 with 8, and so on. Well, in binary, how many digits or bits do I have? Just got 2. So guess who mirrors with 0? And that's it, right? So there is no big mirroring scheme. There's only 2 bits, okay? So anytime I have a 1, what's its mirror? A 0. And anytime I have a 0, it mirrors to become a 1. So they just flip-flop. Yes? Okay. So let's take our number here. All right, so let me take 0, 1, 0, 1, 0, 0, 1, 1. Okay. And I'm going to get the 1's complement. Well, let me write it in English instead of. Okay, so the 1's complement is you just mirror each digit. So what do I get? 1, 0, 1, 0, 1, 1, 0, 0. So all the zeros became 1's and all the 1's became 0's individually. Okay, good. Can I add 1 to that? Okay, and so what do I get if I do that? I get this, right? So it's the flipped version with a 1 added on. Okay, and this number is our 2's complement. Okay, so I claim this number represents negative 83. Okay, so you can think of this procedure as the procedure for how you negate an individual number. Okay, so how do you negate an individual number? Like back in grade school, you just put a minus sign in front. Okay, that's not how we're going to do this in a fixed bit width system. What we do is we say, okay, you take the bit pattern of the positive version, you flip everything and add 1, and that thing represents the negative. Okay, so I started with the representation of 83, and now I have the representation of minus 83. Okay, so what ought to happen if I take the representation of minus 83 and I add it to the representation of 199? What should I get as the answer? The representation of 116, right? So let's see if that in fact happens. Okay, so do we kind of see that what we're trying to accomplish here? Yes. You'd have to do carrying, right? And that didn't happen here, but it could theoretically. So the question was, let's say that this last position, this last bit was a 1, and I added 1, what would happen? I get a 0, and I'd have to carry the 1 to the next position, and I might have to do subsequent carries. Okay, so that could happen. It didn't here. After we finish with this one, let's do an example where that does happen. Okay, so just to illustrate it. Okay, good? Yes? Okay, so let's take the bit pattern that's in orange. Okay, and let's also take the bit pattern that we had from the very beginning as to what 199 was. Okay, good? All right, so what was 199? It was 1, say it again. Okay. Okay, that was 199 that we got at the beginning, right? So we're good with that? Okay, negative 83, the thing we just got from the previous, right at the end that I circled in orange. What was that one again? 1, 0. Okay. Okay, we got that. Okay, so that's just copying down what we had before. Yes? Okay, so now let's add those two. Okay, because remember what I'm doing here is thinking rather than do subtraction, I'm going to do addition of a negative. Okay, so are we cool about the question? All right, so take a moment and add up those two things. Okay, and let's see if we all agree as to what we get. Okay, so I'll do it too. Okay, did we all get this bit pattern? Okay, and the extra one that I've put in the orange box would have spilled over into a ninth position, but we don't have that. So I've just noted that overflow has occurred, and that's the bit pattern we got at the end. Okay. Have we seen this bit pattern before today? Well, what does this bit pattern represent? That represents 116. And let's just double check. Okay. So how do I know it represents 116? Well, what's the far right position? That's the ones place. Do we have a 1? No. Do we have a 2? No. Do I have a 4? Yes. So I got a 4, no 8s. So 4 plus 16 plus 32 plus 64. Add those all up, and what do you get? 116. Voila. Right? Okay. So again, what I've done is this clever representation scheme is how I do negatives. And then I never have to actually do subtraction. I can just think about it as adding a negative. Okay. Does that seem kind of weird? Yes, but you'll get used to it. Okay. Okay. So this system, actually, let me take actually this number and demonstrate one other thing. Yeah. Okay. So I've technically kind of lied here. Um, I shouldn't. I should have picked a different number. So 199. I've mixed apples and oranges here. That bit pattern that I've circled in blue, that represents 199 in the unsigned system. It doesn't represent 199 in the signed system. Okay, let me explain why. First thing to notice is that any number in the signed system that has a 1 in its far left position represents a negative quantity. Okay, but what's true about the bit pattern for 199? It has a 1 in its leftmost position. So if we consider it as a signed quantity, it's actually a negative something. The question is, what is it? Okay, so let me start here. Let me say that I'm going to just call this bit pattern, it represents X, and I don't know what that is. Okay, but I do know that it represents a negative quantity because its leading bit is a 1. Okay. So if I don't know what it represents and I know it's negative, could I make it positive and then see what that represents? Right? So like let's say that I have this mystery number and I take the positive version of it and I get 12. Well, then what did the thing I started with represent? Should have been negative 12. Okay? Make sense? So let's do that. What's the procedure for negating a number in this signed system? What do? Flip the bits and add 1. Okay, so the flipping or mirroring, however you want to call that. Okay, so can I flip these bits? Sure. Can I add 1? Sure. Okay, so whatever we started with, if we call it X, this bit pattern that I've got in the black box represents minus X. Well, first off, the thing in the black box, definitely not a negative quantity, is it? Okay, because its leading bit's not a 1. But what does that represent? Well, I've got a 1, no 2s, no 4s. I've got an 8, a 16, and a 32. So what does that all add up to? Let's see. 8 and 32 is 40, 56, 57. So do we buy that that represents 57? I can do addition correctly, hopefully. Oui? No. Okay. All right. So accordingly, what does that mean about the original number that we started with? This must represent what? If we negated it and we got 57, then this thing should represent negative 57. Okay. Okay. So the lesson from this is if we have 8 bits, we have two choices. We can do a signed version or an unsigned version. A uint we can represent a total of 256 things, 0 up through 255. Signed is just called an int8, so there's no u in front. Okay? And this system, how many things can we represent in it? Well, we're still using 8 bits, right? So how many things can you represent with 8 bits? Still 256 things. But now we have included some of the negatives. Okay, so this is why that example with 199, I really should have changed it, because 199 is not expressible as a signed integer with only 8 bits. You can't do it. You're 1 bit too few. Okay, so that was a bad example. That's my bad. I mean, they'll just hire anybody to teach here. You go to IU or even the school to the south, and the dining hall's better. I'm sure the professors are better. The football team may not be better, but right. Yeah. Okay. So now, why is negative 128 through 127 actually 256 things? Because zero's in the middle, right? We still got to count that. Okay. So this procedure of flipping and adding 1, so that's called taking the 2's complement of the number, that works for every number with 2 kind of weird exceptions. One of them which is less weird than the other. Okay. The first weird one would be, what would happen if I took all zeros and I flip that and I add 1? Well, what happens if I flip all zeros? They all become 1s. If I add 1 to that, what happens? I get all zeros in an overflow bit. Okay? So if I mirrored or did this 2's complement procedure with all zeros, I'd end up with all zeros. Does that make sense that that ought to happen? Yes or no? Well, okay, what does all zeros represent? And if this procedure is equivalent to negating something, what's negative 0? Still 0, right? So this procedure ought to give us the exact same thing back because 0 is its own negative, right? Yeah, 0 is its own negative. There's nothing to do there. Okay, so yeah, it may seem weird at first, um, but in fact, it's not when you think about it that way. Okay, but there's a second answer to this question. Okay, so essentially, what I've asked here is, what number, if you add it to yourself, do you get 0? Right? 0 certainly did the job, and that's obvious, right? Even grade school kids would say that. But there's a second answer here, and it's actually minus 128. Okay, so first off, let's figure out what the bit pattern is for minus 128. Okay, and in order to do that, it's 1 followed by all zeros. Okay, now let me demonstrate why I know that this is correct. I claim that this represents minus 128. What would negative 128 plus negative 128 be? So if I added it to itself, what would I get? Negative 256. Okay. Now, every number, if it ever exceeds, well, period, is really equivalent to the remainder upon division by 256. Well, what's the remainder upon division of negative 256 by 256? 0. Okay. So negative 128 plus itself equals 0. It's weird. Okay. So if I flip all the bits here, what do I get? I get that. If I add 1, I get 1 followed by all zeros because of a bunch of carries. But that's exactly what I started with. Okay, so I have a number here that represents something. Do we agree that the number is definitely not 0? Yeah, how do I know that this number is definitely not 0? Because there's not just all zeros there, okay? I mean, it's somewhat logical to think that 0 is just a bunch of zeros, and anything that has ones in it is, well, not 0. Okay, does that sound reasonable? Okay, so whatever this is, I claim it's minus 128, okay, but it's definitely not 0. I've negated it, and I got itself, okay? So what would negative 128 be? 128, but does 128 exist in my range of numbers? No, okay? So this is the weird one, okay? And notice that this is the biggest negative number that we can represent. The most negative number, okay? That's the weird one, where if you do this procedure, you'll get the same thing back, but the number isn't 0, okay? And 0 and this one are the only two numbers for which that happens. Everything else works really nicely. Okay, so these are the exceptions. Okay, so basically what we now know how to do, okay, is how to represent negatives and also how to do, therefore, subtraction. If I want to do subtraction, I think about it as adding the negative. So first figure out the negative and then do the addition. Okay. The other thing, though, to notice is that the answers don't always match what they would from grade school. Okay. And the reason is we are constrained to always being either within 0 through 255 for unsigned or minus 128 through 127 for signed. And if you go bigger than 127, you actually wrap around and start counting again from the bottom, the same way that the numbers sort of wrap around on the clock. Okay, so if you think of this as a clock with 256 different positions, it's the exact same thing as our normal clock that only has 12. Okay, it's weird, I'll grant, but that's the way computers do arithmetic. Okay, now, would you guys agree that this overflow thing is kind of a problem, or could be a problem? Because you don't get the answers you expect you're going to get. Okay, if you understand that this can happen and you take steps to deal with it when it does, okay, then that's good coding. But sometimes even really, really smart people screw this up. Okay, YouTube did with the Gangnam Style video, right? They were using 32 bits, and so the maximum, their stuff could go from minus 2.1 whatever billion up through 2.1 whatever billion, and it exceeded and overflowed, and suddenly they had a negative play count for the Gangnam Style video. Okay, did anybody die because of that? No, it was a big mess, and I'm sure there were lots of headaches and, you know, the next weekend, everybody going to the bar and being like, oh man, we were idiots, right? But nobody died because of that. There are situations, though, where imprecisions and overflows like this have killed people. And I think we would agree that people dying is generally a bad thing. Okay, so actually, one of the things next week on Friday we'll talk about is we're going to have a discussion over some readings about several situations in which overflow and precision errors cause death or explosions or other horrible things. Okay. The other thing is on Friday next week we will there's going to be a film crew on campus, and they want to get some good video of like math and science and computer science people doing cool stuff. So naturally, they called me, right? Um, and so we'll spend about 10 or 15 minutes of you guys sort of demonstrating the final circuit project, which I'll post to Canvas this afternoon, um, getting cool video, and then we'll also do the discussion stuff. Okay? All right. We will continue on Friday with floating point.